Here we have a bipolar junction transistor, a current voltage curve that I measured in the lab. This one right here is for the input section of the transistor. It is measuring IB on the y-axis and VBE on the x-axis, where IB is defined positively into the base and VBE is the voltage at the base minus the voltage at the emitter. IB can be written, thanks to Shockley, as IS times the quantity e to the q VBE over NKT minus 1. Here we've picked N to be approximately 1, since this is a silicon transistor. The base emitter junction is forward biased, which means that VBE is positive here. That means that the exponential here is going to be much larger than 1. And in this case, we can ignore the 1, giving us this simpler expression over here, which is simply exponential. Notice that the current rises steeply at about 0.7 volts right here. So that this line right here with the arrow on it is not a bad approximation for the curve in green over here. And the expression for this line would simply be VBE is approximately 0.7 volts. Let's have a look at the output IV characteristic curve. Here we see a whole family of characteristic curves for the output. Notice that we have IC on the y-axis and VCE on the x-axis. IC is labeled as positively going into the collector, and VCE here is the voltage at the collector minus the voltage at the emitter. IB is labeled as before. This whole family of curves is one for each base current. The bottom one here, which you see almost right along the IC equals 0 line, is for IB equals 0. The next one up here is for IB equals 2 microamps. The next one after that is IB equals 4 microamps. This next one is IB equals 6 microamps. This one is IB equals 8 microamps. And this one right here underneath the black arrow is IB equals 10 microamps. Notice that each of these curves is almost exactly flat. And a line such as this black one that is exactly flat could be written as IC equals a certain value, in this case 0.5 milliamps. Or in general, for all of the base currents, we could write it as IC equals beta times IB. And the beta number is approximately constant because each of these curves, as you moved it up by 2 microamps, jumped up by 1 division. And so you can see the number beta, which would be the IC divided by the IB, is approximately 50. Let's see if we could make a simple model for this NPN bipolar junction transistor in the active region. Here we have a schematic of the transistor with the values IC, VCE, IB, and VBE labeled as before. Over on the right here, we have our first stab at a model. Notice for the base emitter junction area, we modeled it simply as a 0.7 volt voltage source, which came from the approximation of this curve in green by this line in black, which was given by this equation, VBE equals 0.7 volts. On the output side, we notice that the collector current, IC, could be written as a value beta times IB. And that is a current source with value beta times IB, which is a current-dependent current source, as we've written right here, with value beta IB. Putting these two together yields the simple model that most people use to understand how a BJT transistor circuit in the active region works.